Boa tarde a todos, bem-vindos ao ciclo de seminários do Departamento de Geofísica do IAG USP. Hoje a gente tem o prazer de receber o Santiago Soler, ele acabou de defender o doutorado na Universidade Nacional de San Juan, doutorado em Geofísica. Ele é um físico formado pela Universidade de Rosário e atualmente ele trabalhou durante o doutorado, continua trabalhando como um dos desenvolvedores do projeto Fatiando a Terra, nos quais eles mantêm bibliotecas em Python para usos em geosciência. Bom, a pesquisa dele é focada principalmente no processamento e modelagem de dados gravimétricos e magnéticos, criando novas metodologias e sempre focado na elaboração de códigos abertos. Agora ele acabou de defender o doutorado e vai começar a trabalhar como pós-doc na University of British Columbia, no Canadá, e ele deve ir daqui a pouco tempo. Eu participei da banca dele de doutorado, foi bem interessante o trabalho, por isso que eu quis convidá-lo para apresentar para vocês também o que ele tem feito, junto com o pessoal do Fatiando a Terra. Então, thank you, Santiago, for accepting our invitation. Feel free to begin when you want. Thank you.
Okay. Hello, everyone, and thank you, Gabriel, for the invitation. It's a pleasure to be here with you. So I'm going to start the presentation that I titled Empowering Science with Open Source Software. And if you want to see the slides on a different screen, you can get them by scanning this QR code or by going into this link in your browser. And yeah, you can enjoy them on another screen or anytime you want. So, like a brief introduction, besides what Gabriel said before, I'm a physicist and recently a PhD in geophysics. I'm also a Python developer, working mostly in Fatiando Terra. And I'm also a member of the computer-oriented geoscience lab, where I did a lot of research lately. So for this talk, I wanted to do some time travel and go back to do some career retrospective and see what were the motivations and for me during my career and how I got where I am today. So I would like to jump to Rosario, which is my birth city. Here I was born, I was raised, and it's a beautiful city. Has the flag memorial as the main attraction, but it's a city that is on the shore of the Paraná River, which you can always enjoy. You can navigate the river by boat. This is an activity that most of us do, and actually, this is my photo on my own boat, and you can see a lot of stuff if you want to paddle for a long time. For example, these are irupes, which are a water lilies that could grow up to 2 meters of diameter, and yeah, a lot of animals as well. So here I went to university. I did a licentiate degree in physics at the Universidad Nacional de Rosario. And during this degree, we had a lot of maths and physics, of course. We did some cool experiments like this one, which is a plasma of nitrogen being probed with a very thin tungsten wire. And I also learned how to code. On the left, you can see a Fortran code for Newton-Raphson implementation. And on the right, there is what could be my first neural network written in C. So that's what I learned back then. But also during my experience in this degree, we had a very welcoming student environment that allow us to do a lot of stuff besides what's in the curriculum, besides going to class and giving exams. For instance, we organized seminars, students where other students could prepare some talks, and we also invited teachers and also graduate students, and we had a lot of fun doing so. Another thing we did was setting up our own computer lab from scrap computers from different research labs. Um, and by doing so, we learned a lot more about free software, like GNU Linux distributions and different kind of software like LibreOffice. We also learned LaTeX and doing all the lab reports with it. And just a side note, when I talk with free software or open software, I'm meaning free software as in free speech and not as in free beer. So, in summary, I think that university, we always conceive university as a place that we could shape and to 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 fulfill our needs and to achieve different goals. So, if I would have to summarize my whole experience during my licentiate degree in a few sentences, is that we always try to explore outside the curriculum. We try to shape our environment according to our needs and goals, and we did it by community, inside a community, which was the students of physics, where it was a very tight community from all across the career, from junior to senior, and we also had a lot of fun doing so. So let's fast forward a little bit right now, and let's move from Rosario to San Juan, which is a city on the west of the country. And it's a very beautiful city, smaller than Rosario, and but has a lot of nature attractions you can visit. For instance, there are very high mountains. If you are into mountaineering, this is an awesome place to be, with a lot of nature attractions that, yeah, I completely recommend. Yeah, you can go to high mountains if you want to, and also do some rock climbing if you're into that too. Oh, and if you happen to be there in San Juan on 2019, you could experience the eclipse with during 2 minutes. Um, so in San Juan, I went there to finish my licentiate degree and do my licentiate thesis, and I arrived at the Instituto Geofísico Sismológico Volponi. And in there, I started learning a lot about geophysics and especially about gravity and magnetics. But I noticed something that in potential fields, most of the researchers use expensive private software to do their research, to process and model their data. And I found a few problems with that. Uh, First of all, I found it very hard to make reproducible science with this particular software, not only because of the private and expensive nature of it, but also because of the all the GUIs that are built. In order to get a certain process, you have to go around different menus, and it's very hard to remember what those selections were and keep track of those. And second thing is that it was really hard to study the code because we can access to it. So I cannot learn from what other developers were doing and what the code was actually doing with my data. And because of that, I cannot build on top. So if I would like to create a new method, I will have to, uh, I couldn't write it using those tools. So one possible solution to that is to write my own code, right? So I already know how to code in Fortran and in C, but the licentiate thesis was only between 6 months and 12 months, and I didn't have the time to code, to generate a thesis and write a full code in these two languages. But a few months before that, I did an online course on statistical mechanics in which I learned how to code in Python. And then I thought that, yeah, I can code faster in Python and I can do it. But what if someone already coded something like this, like the tools I need? And I went to my uh, favorite search engine back then, and I would probably did something like this and found the Fatiando Terra version 0.3 website. So Fatiando was a project written in Python. It was open source, and it was all about geophysical modeling and inversion. This is what I was looking for, right? So the project was mainly developed by Leonardo Ulleda, who is a bachelor and master in geophysics, graduated at USP, and he's also a PhD in geophysics from the Observatorio Nacional. And today he works as a lecturer at the University of Liverpool, and he's an open source software developer working on multiple projects like Fatiando, GMT, and also PyGMT, which brings all the power of GMT into Python. So with Python plus the whole scientific stack around it and Fatiando, I managed to finish the licentiate thesis. But meanwhile, I was also doing my first contribution to the project. Here I have what could be my first PR merge into that, uh, which implements a function to calculate radial average power spectrum to over two-dimensional grids. So I really like the experience of writing code and doing research in geophysics, so I decided to start my PhD in geophysics. And I have been lucky enough to have Mario Jimenez as advisor. He's a researcher from San Juan. And I was lucky to have Leonardo as my co-advisor. So one of the goals of the thesis was to model tesseraoids with variable densities. But what are the tesseraoid? So a tesseraoid is basically a 3D body that resembles a prism, but it's defined in spherical coordinates. So it's a portion of the space that is defined between two latitude angles to longitude angles and the two surfaces of two concentric spheres of different radii. Um, and the main challenge of tesseraoids is that the gravity fields a tesseraoid generate on any observation point doesn't have an analytical solution. So we have to numerical approximate it. And the main challenge of considering variable density tesseraoids is now the numerical approximation had to take into account the variability of that density. And it was an open problem back then when I started my PhD. So we jump into it. And after some work, we solved it and created a new method that was built on top of the existing tesseract implementation in Fatiando. We managed to publish it in Geophysical Journal International back in 2019. And also, I uploaded a preprint to Earth Archive so anyone can download it for free. And all the code for that paper is in a GitHub repository if you want to take a look. It's under open source license. So yeah, basically you can do whatever you want with it if you follow the license. But that wasn't enough because we wanted that scientists would have an easier way to use this new method besides cloning that repository and figuring out how to install and how to use that particular software that was developed for the paper. And the idea was to include that implementation into Fatiando. But what was going on Fatiando back then? Well, the whole geoscientific stack has changed quite a lot from the beginnings of Fatiando. A lot of different new libraries were being created, like Simpeg by Gimbly, GenPy, and different tools for visualizing data, like by GMT, by Vista, and integration between these libraries like Subsurface. So the ecosystem was shifting, right, and was changing a lot. And in Fatiando, we didn't want to overlap with any of the other projects. So the old Fatiando package was finally deprecated, and instead a new Fatiando was born. So instead of having a single library hosting all the tools, we decided to split this project into several smaller libraries with a specific goal for each one. We applied better coding practices and started using modern tools. And the whole goal of this was to supplement the ecosystem and not overlap with other tools. So, for instance, some of the tools we have today are Push, which is a small package for download and cache data, Verde, which is a tool for processing and reading data with an interface inspired on scikit-learn, which is the machine learning toolkit on Python. We also have Bool that defines several reference ellipsoid and allow us to compute normal gravity. We also have Ensayo, which is I think the latest one, and this one allow us to download some particular data set that are very good to use in our documentation or in tutorials, or even to probe some code you might have. And lastly, we have Harmonica, which hosts all the features for doing processing and modeling of gravity and magnetic data. And I'm currently the lead developer of Harmonica. So, wait a second. So the goal was to implement the variable density tesserates into Harmonica, and we managed to do so. And here I can show you a very simple example on how to use that particular implementation. So we can start by importing some packages, and then we can define the mean radius of the WGS84 ellipsoid, and we can get that ellipsoid from Bool. And next we can define a single tesseract just for this example, and we can do so by defining the boundaries of the tesseract. That would be the west, east, south, north, bottom, top boundaries. And because we are going to compute variable density, so we are going to compute the gravity fields of this variable density tesseract, we need to define a density function for it. And here I'm just defining a very simple linear function. And then once I define the density function as a regular Python function, I need to define the computation points, which in this case are a grid. And then finally, I will call the tesseract underscore gravity function by passing the coordinates. That would be the computation points, the tesseract, and the density function. So the way I see this process is that we started by tackling a scientific problem by building on top of the open source tools we already have. And then once the science had been done and published, we incorporated that particular method into the same tool we've been using to develop that science. So the way I see is that we're empowering science with open source software, but we are also empowering open source software with science, creating this feedback relationship between both of them. And a similar story happened with the following research, which is the gradient boosted equivalent sources, or in other words, how to interpolate 2 million gravity data points. And we also published that paper last year in Geophysical Journal International as well. And we have also implemented that particular method into Harmonica under the equivalent sources GB class that anyone can use right now. So besides the two papers, and after some more work, I finally finished my PhD. But during that road, I wasn't alone. I was participating in a lot of different communities. First, like the Fatiando community, which includes all the developers, contributors, and users of Fatiando. And I've been also participating in Software Underground, which is a great community for people who loves rocks and computers. And they do these great events that are called Transform, where a lot of tutorials are being uploaded to YouTube, so anyone can see them anytime you want. Um, I've also participated in the computer-oriented geoscience lab, which is the lab that Leonardo created, and where most of the work I've been doing was inside that. And there's a lot of young people in there doing some very exciting projects that I'm looking forward to the evolution of the lab. I've also participated in Geolatinas, which is a very awesome community for any Latin American people out there that want to join. And I've also been in touch with the Carpentries, which is a very good organization that creates a lot of teaching material and also trains people to be better teachers. So I really appreciate all the interaction I had during with all of these communities. So if I would have again to summarize my experience during my PhD, is that besides the main goals of the PhD, I've always tried to explore outside the curriculum, outside that particular goals, outside the courses I was attending to. I always try to shape my environment, creating new tools, engaging with different people, and trying to build upon that. And as I mentioned before, I did it in community. And of course, I tried always to have fun while doing so. So right now, I want to go and do some demo time on some of the tools we have in Fatiando. Um, so I will jump into another tab of my browser, and here's a Jupyter Lab instance so that I'm running. And I have this notebook that I have somewhat prepared. So the main goal of this is I'm going to show you very quickly how to process gravity data with Fatiando right now. And so I will start with importing some packages. These are very common packages in the Python scientific ecosystem, and these are the Fatiando libraries I mentioned before. So let's start by importing it. And the first thing I'm going to do is to download some gravity data from the Bushveld Igneous Complex in Southern Africa. And I will use ensayo for that. So I will call fname equals to ensayo.fetch Bushveld gravity, and I will download the version 1 of the data. And if you run this, ensayo will download that particular file. But if you already have it in your computer, it will just return the path to it. So then I will load that data with pandas because it's a CSV file. And as you can see, my data has 5 different columns for the longitude and latitude of each observation point. 1 column for the height over the sea level, and 1 column for the same height but at a geometric height. And lastly, the gravity observation. So we can use PyGMT to plot these points. And as you can see, they are roughly all around the 9.8 meters per second square. So next, what I'm going to do is I'm going to download a DEM of the Southern Africa from eTopo, but I'm going to use Ensayo as well. So let's run this. And again, because I already have it on my computer, it's just returning the path to it. And I would load this topographic grid using Xarray. So as you can see, this topography is a two-dimensional array in defining latitude and longitude coordinates. So next, what I want to do is to crop this topography grid to the region around the Bushveld Igneous Complex. So I will start by getting the region of my data. So I would use verde for that. And there is a particular function called getRegion. And I need to pass the longitude and the latitude of the data. And I get the region in west, east, south, north, and then I want to pad it because I don't want exactly to crop the topography to the same area, but a slightly bigger one. So I would define region pad equals to verde dot pad region, and I need to pass the region and also how much I want to pad it. So let's pad it by 1 degree. So if I print the region pad, here you can see that it's slightly bigger. So then I can use Xarray to crop it, and then I can plot this topography using PyGMT. And as you can see, here is where the data is located, and it's slightly bigger. Okay, so next stop is to compute the gravity disturbance. The gravity disturbance is defined as the observed gravity minus the normal gravity, which is the gravity generated by the reference ellipsoid. So I'm going to use the WGS84 ellipsoid for this, and I can use bool to get it. So I will define ellipsoid equal to bool.wgs84, and then I can compute the normal gravity that this ellipsoid generates. Normal gravity. And I want to compute it on every observation point. So I need to pass the latitude of my observation points and the height. Yeah. And I'm going to use the geometric height for that. And once I compute it, I could subtract the normal gravity from the observed gravity. So that would be data dot gravity millival minus normal gravity. And I will save it into the data frame I already have. Right? So I can plot the gravity disturbance using PyGMT. And yeah, here is the gravity disturbance over the Bushveld igneous complex area. But one common step to do while processing gravity data is to remove the effect of the terrain, because this the gravity disturbance is highly affected by it. So we are going to use that topography grid we already cropped to do that. And first I need to do some stuff. For instance, my topography grid is defined in geographic coordinates, and for the thing I'm going to do right now, I need it in Cartesian coordinates. So I'm going to use PyProj to project it. So I'm projection, project the data, and then save it.
Santiago, a moment. I think you are covering your mic with your hand because the sound is not good when you type. Okay. I don't know if it...
Okay.
Well, now it's okay now.
Okay.
It's why you type, so I think that maybe your hand's covering it. I don't know.
Okay, yeah, probably. Okay. Thanks. So I just projected the data and saved the easting and northing columns in the data frame. And now what I can do is to project the grid, and I can use Verde for that with the project grid function. And I'm going to call it. And here I have the same topography grid, roughly. But now, instead of being defined latitude and longitude, it's defined northing and easting. So what I want to do is to compute the terrain effect. That would be the effect of the topography. And I'm going to do it by forward modeling a set of rectangular prisms. Okay. So what I need to do is to first define a prism layer for it. So I can put topo model equal harmonica.prism layer. And first of all, I would need the coordinates of the distance. That would be each one of the points in the topography grid. So I would be topo plane dot easting and topo plane dot northing. and I need to define the surface of the layer, and that would be basically the double plane. And as a reference, I'm going to set zero height. And one more thing is that I need to assign a density to each one of these prisms. So I'm going to define properties equal to density. And I need to do is to define this density array. Okay, so let's assign a value of 2670 for each of the prisms that are above the reference, and to anyone that is below, we are going to assume that is water.
Santiago, may I interrupt you again? Because whenever you type, the sound is really bad. Leonardo suggested to turn your video off. Maybe it's a bandwidth problem. I don't know. We could try that.
Okay. So what are you saying? Sorry.
Yes, because your sound is really bad while you are typing. So Leonardo suggested to turn off your video. Maybe it's a bandwidth problem.
Okay.
Okay, let's try again.
Okay. So I'm going to define the density to be sorry, and plane.
No, it's continuous.
Okay. So I'm going to do this. I'm going to type and then talk.
Yes, okay, that
Okay.
would be perfect.
So I'm going to define the topo plane, and where is higher than 0, I'm going to put 2670 for the density, and otherwise I'm going to put the density contrast of water. So that would be sorry. Okay, what is the problem? The next is to compute the gravitational effect of the terrain. And this might take a while, but I can do it. I need to define the coordinates on which I want to compute this effect. So let's define out those coordinates as the same as the observation points.
Santiago, Leonardo suggested it's noise suppression that's causing problems. So I don't know if it's easy to deactivate noise suppression.
Let me see. It would be in the yeah, I don't see noise suppression in the
Yeah, I don't see it either. I'm trying to find it here.
yeah. Okay, let's do this. I'm going to run this cell, and because it will take 1 minute, and then
Okay,
while
okay.
the computing runs, I will try to solve it. Okay, so I'm going to type here. Sorry, I forgot to add this. It's here, and then I'm going to run it. Oh, sorry, typo here. Okay, this might take a while, take 1 minute. I just wanted to show you that this code is using all my CPUs. It's running in parallel, so that makes it a lot faster than running a single core, and that's why you're seeing 100% of on every CPU I have in this computer. While we wait, I'll try to improve the audio. Um, Gabriel, are you there?
Yes.
Yeah, okay. I don't see any way to improve that or to disable noise reduction.
Yes, I couldn't find it either. Let me ask if Leonardo
Okay.
knows.
I just need to type 2 cells and that's it, or maybe 1. So I will try to do the same, like not talking while typing.
Okay. Yes, now it's perfect. But as soon as you begin to type it, it becomes horrible.
Okay. So once we already have the terrain effect, we need to remove it from the gravity disturbance to compute the Bouguer anomaly or the Bouguer disturbance, and we can plot it. And as you can see, the Bouguer gravity disturbance is highly affected by this regional field, probably with negative densities, that is generated from the MOHO. So one thing we could do is split between the residuals and the regional field, and we can do it by defining equivalent sources, very deep equivalent sources that generate this regional field. So I could use harmonica to do it. So I will define deep sources using the equivalent sources class in harmonica. I'm putting very deep sources at 1,000 kilometers deep. I'm going to fit the coefficients of those sources using the Bouguer gravity disturbance we already computed. And once those are fitted, I'm going to define the regional field by predicting the field that these deep sources generate on every computation point. And then I will define the residuals as the difference between the Bouguer gravity disturbance and this regional field. And it's a data frame and plot it. So now you can see the gravitational effect of only the shallower sources, right? And as a final step, I'm going to grid these scatter points into a regular grid using the same technique, the equivalent sources. But now I'm going to define shallow equivalent sources, not that deep, so they can reproduce the field of these shallow sources. So I'm going to run this by creating the sources and fitting them against the residuals. And what I'm going to do is to define the target grid I want to compute it. And I'm going to do it in geographic coordinates. And then I'm going to use the grid method uh, to compute the effect of these sources on this regular grid. And I'm going to pass the same projection I used to project the data. So this way, my target grid isn't defined in geographic coordinates, but all the computation is done in Cartesian. I'm going to run this. And finally, I want to show you how this looks like, and just to compare it with some knowledge of the geology of the same area. You can see these 3 positive lobes, which correlates with the 3 lobes that are known from the geology of the area. So I'm going to go back to the slides. If you want to take a look at all this process again, there is a full tutorial of 2 hours I gave at Transform last year. So that's there is a video for that, and there is also an updated notebook of that tutorial if you want to take a look. So let's jump into the future and how do I envision the future. Today, every open source software behind every major scientific breakthrough, like the first photograph to a black hole, or even flying objects in different planets that are using open source software to work. Um, so my idea of the future is that the science will be on top of these four legs, using open source software to process data and to create the scientific results we need, working with fair data that will be findable, accessible, interoperable, and reusable data. And that doesn't mean um, available for use, but with an actual license. Uh, I expect that scientific publication would be all open access, so anyone can read them and work on them. And kind of a stretch here, but I would love to see that the hardware we use for science, all the instruments we are using for making observations, would be open hardware, so we can not only fix them but also improve it if we need to. But the main problem that is avoiding us to get to that future is that open source software and all the open science has very poor recognition and funding. And but there are things that we can do. So for instance, if you already have a code that you have been working on your research, share it under open source licenses. uh, your code doesn't need to be the perfect code, but any code is better than no code. The other thing we can do is cite the software we use. That helps a lot for the software developers to get funding for their projects, right? Another thing you can do is, if you are in a position where you have to evaluate grant applications or job applications, value the open source software development. And another thing we can all do is that if we can, we can also fund open source software development. But if you are not in position to do that, you can start by learning. There are a lot of places you can start, but the Carpentries is a great one. So in there you can learn a lot about how to code, but also how to use different tools that developers use daily for doing a quality software development. uh, you can always get involved in different communities. I'm just naming Fatiando community or Software Underground or GeoLatinas for an example, but showing whatever community you might feel welcome. And also contribute. You don't need to be an expert on software nor on your science domain. And not everything is about code. If you don't feel like you have the level to contribute with some piece of code, there are a lot of stuff you can do on projects, like improving the documentation, reporting bugs, asking for features, bringing new use cases for the code, etc. And you can find projects that has contributed guidelines that are awesome because they're very detailed steps you need to follow in order to contribute. And I think that the best way to learn how to develop software is by getting involved in a larger project. So getting more personal here, what is my future up to? Well, I'm going to start a postdoc soon. I'm going to be working at UBC, that's the University of British Columbia, and mostly on the application of gravity and magnetics to carbon capture. I'm going to be supervised by Lindsay Higgy, who has also been working a lot on SIMPEC, which is another great project for inversions. And part of my work would be to to improve all the interactions between SIMPEG and particularly Fatiando. So my future is full of open source software development beside my research, and I would hope to be exploring, shaping my environment, doing it in the community, and of course having fun. So thank you, and here are some links if you want to contact me. Feel free to do so.
Thank you for the presentation, Santiago. Unfortunately, we had this small problem during the typing section. Well, it's very interesting. Thank you again. I have seen something during your defense of your thesis. It was all very interesting, and now I could see other stuff. I think that the part you gave that example, it's not a problem because you said there is a video doing the same thing. So if anyone is interested, they could look after that. We could accompany, but we couldn't understand everything that you said. So let me see if there is any question. You can write in the YouTube chat and I'll read it to Santiago. Okay, Victor Sasek and Leonardo Ieda, they're saying thank you.
Thanks both. Yeah, some promotion in there. Victor is doing some awesome work, sharing some great code for geophysical, for geodynamic modeling. So go check it out. It's Mandiok.
Those data you presented from the Bushveld complex, it's just an example, or do you have a work based on that?
No, it's just an example. I don't have any research on that, I think.
Okay.
But now that you mention it, I think I used that particular dataset to create synthetic surveys for the last paper. So
I remember that. Yes.
Yeah, I haven't used that particular data, but I have used the layout of the points to build synthetic surveys.
Okay. Well, people are mostly thanking you. Yeah. So I think that there is no question. I myself am really happy to see your presentation, and I think it's all. So I think we could end here. If okay.
Yeah, for sure.
Well, thank you then, Santiago. Thank you. Good luck in your next step now in your postdoc. I hope to hear soon from you and maybe invite you to another presentation in a year, who knows. So we'll keep in touch and maybe you'll come back and do another presentation.
Yeah, for sure. I'll be glad. And thank you again for the invitation. It was really fun. And yeah, hopefully it wasn't that bad with all the typing and the microphone.
Yeah. Okay, thank you. And thank you everyone for watching.
See you next time.
See you.